BLE SoC SDK Overview Introduction. Today, I will provide you with an overview of the Realtek BLE SoC SDK resources, helping users quickly understand the advantages and features of the BLE SoC SDK, and aiding developers in effectively utilizing these resources for project development. Furthermore, I will detail the basic platform components related to the development process, including getting started, memory management, interrupts, low power modes, download, and debugging systems. A software development kit, SDK, is a package used for developing applications, providing the necessary tools, documentation, and sample code. It includes the core functionalities and APIs required for application development, thereby simplifying the development process. In the mass-produced BLE SoC series, the RTL87X2C, RTL87X2D, RTL87X2E, and RTL87X2H use the same form of SDK development package, while RTL87X2G has slight adjustments. Below is an introduction to the contents of the two types of SDK development packages. For the SDK package of RTL87X2C, RTL87X2D, RTL87X2E, and RTL87X2H, the top-level directory includes the following contents. Doc, SDK documentation. Bin, binary files for linking user applications. Inc, interface header files exported from ROM. SRC, source files of sample projects. Board, reference sample projects, including examples of I/O and Bluetooth. Tool. A toolkit that supports extension feature development, user application creation, and mass production. For the RTL87X2G SDK package, the top-level directory contains the following contents with the following adjustments. Doc, SDK documentation. Bin, binary files for linking user applications. Include, interface header files exported from ROM. BSP, files related to board-level and hardware-specific aspects. SoC, software protocols that are upper-layer and hardware-independent. Samples, reference sample projects, including I/O and Bluetooth examples. Tools, a toolkit for developing extended functionalities, creating user applications, and large-scale production. The main difference between the two SDK packages is that RTL87X2G removes the original SRC directory and further divides it into BSP and SoCs based on the application level of different modules. In summary, the Realtek BLE SoC SDK offers comprehensive documentation, application sample projects, and toolsets to help you fully leverage the advantages of the SDK. Getting started with the BLE SoC SDK requires the following components. 1. SDK package. This includes comprehensive documentation, examples, and tools. 2. Evaluation board kit. This is a toolkit containing the necessary hardware devices for evaluating and developing new products or technologies. 3. Download and installation of the development environment. Currently, the BLE SoC series supports different compilation systems and platforms, as indicated in the table below. 1. Supported on the Windows platform with the Kiel UVision integrated development environment, compatible with ARM/ARM compilers. 2. Supported on Win Linux Mac platforms with GCC compilation based on Makefile. 3. Deployment is underway to support GCC/ARM/ARMCC on the Win Linux Mac platforms within the VS Code integrated development environment. 1. All applications in the SDK can be compiled and used with the Kiel Microcontroller Development Kit, MDK. Therefore, before starting software development, developers should obtain and correctly install Kiel. The toolchain version is displayed on the screen, and it is recommended to use this version or a higher version to avoid any compatibility issues between the ROM executable programs and user applications. 2. For developers who require in-depth and comprehensive debugging, JLink is an indispensable tool. It is recommended to install version 6.44 or newer. 3. It is generally not recommended to create a new project for development. Instead, it is better to open an existing demo project and add the developer's own function codes to it. 4. By correctly setting Keel's flash download algorithm, you can directly use Keel for file burning and debugging. 1. Applications in the SDK can be compiled and used with GNU toolchain. So before starting software development, GCC ARM NunEB should be obtained and installed correctly by users themselves. Please visit the URL displayed on the screen for more information. GCC ARM NunEB 10-2020 Q4 Major Win32, or newer version, is highly recommended for installation. 2. The MinGW is used to parse makefile. Please visit the URL displayed on the screen. Version 3.82.90, or newer, version is highly recommended for installation. 3. The sample GCC projects that can be directly used in the SDK are based on makefiles. Before compiling a GCC project, it is necessary to correctly configure the related environment variables and then compile the project using the make command. Hardware block of BLE SoC includes Clock Management Unit, Power Management Unit, RF Module, Rich Peripherals, Flexible RAM Configuration. For more details, please refer to BLE SoC Hardware Introduction. The software architecture consists of several major components. Platform includes OTA, Flash, FTL, and other components. I/O drivers provide application layer access to the interface of BLE SoC peripherals. OS kernel, FreeRTOS, is integrated by default in ROM and supports the development of applications to replace other operating systems such as RT-Thread, Zephyr, etc., to meet specific application requirements. This flexibility allows developers to choose the operating system that best suits their application based on actual needs. OSIF, abstraction layer for real-time operating systems. GAP, abstraction layer through which user applications communicate with the BLE stack. Due to the different production times of different ICs, the versions of FreeRTOS integrated by default in the ROM may vary. Detailed information is shown in the table below. It consists of the following components: task management, queue management, interrupt management, resource management, memory management, time management. Task management is responsible for creating, scheduling, and executing tasks. Queue management is used for inter-task communication. Interrupt management handles external interrupt events. Resource management tracks the allocation and release of system resources. Memory management is responsible for dynamically allocating and releasing memory. And time management provides timing and delay functions. The functional synergy of these components ensures the stability and efficiency of the operating system. The FreeRTOS integrated in ROM by default automatically creates timer task and idle task, and the Bluetooth protocol stack will create multiple tasks. Additional tasks can be created based on application requirements. It is recommended to set the priority of application tasks according to the following table. The OSIF layer is designed to offer a standardized and uniform RTOS API set by encapsulating the specific RTOS interfaces. Vendors have the option to incorporate their own RTOS implementation within the OSIF layer, but without altering any upper layer software components. It is highly recommended to utilize the OSIF API during software development rather than directly accessing the specific RTOS interfaces. This approach enhances code portability and facilitates easier transitions between different RTOS implementations without necessitating extensive modifications to the software components. The RTL87X2G uses the Real_M300V processor, which is equivalent to ARM Cortex-M55 and supports ARM TrustZone functionality. Compared to ARM-v7M, the processor state is divided into secure execution state and non-secure execution state. These states are orthogonal to the thread and interrupt models, allowing operation in both secure and non-secure states. This provides several advantages. 1. Security. TrustZone technology isolates secure and non-secure areas through hardware, protecting critical data and code from malicious software and attacks. 2. Privacy protection. TrustZone ensures that sensitive data and user privacy are protected from unauthorized access. 3. Secure execution environment. TrustZone provides a trusted execution environment to ensure software security and integrity, preventing malicious software tampering and destruction. 4. Energy efficiency. TrustZone technology can effectively manage the use of system resources, improving system energy efficiency and performance. 5. Secure boot. TrustZone ensures that the system is not susceptible to attacks by malicious software during the boot process, guaranteeing system security and reliability. When the system powers on or is reset, the boot flow will be executed. The boot flow includes the following steps. 1. eFuse validation. 2. Security control according to eFuse value. 3. Flash image check and execute. Security control is implemented on all BLE SoCs except on RTL87X2E. eFuse verification determines whether to enable secure boot. If secure boot is enabled, image authentication will involve signature, CMAC, and secure version verification. For more details, refer to the security introduction. Flash image check and execute means checking all types of flash images and executing them. The process includes 1. Checking OEM data, flash layout is included in this file. 2. Checking if a valid upgraded image exists in flash. 3. Checking OTA bank header files. 4. Checking every flash image in OTA bank. 5. Executing image. To assist in creating user applications, many sample projects have been included in the SDK to start with, such as BLE_peripheral and some BLE-related demo sample projects. By studying these sample projects, users can easily become familiar with the SDK. Brief description of application flow. System is initialized in main function, including board, peripherals, BT stack, profile, power mechanism, task, etc. Introduce some procedures. Board init contains initialization of pinmux settings and pad settings. Gap init contains initialization of gap-related parameters. Profile init contains initialization of BLE profiles. Power Manager init contains initialization of power management related. SW Timer init contains initialization of SW timers. AppQ init contains initialization of AppQ. Driver init contains initialization of peripherals. In application task, BT stack, profiles and peripheral drivers are initialized, and I/O MSG mechanism is implemented. All functions are packaged into I/O events, and the events are handled in related MSG handlers. BT stack message is packaged into BT I/O event, which will be handled in the same way as peripherals. BT stack, profiles and peripheral drivers are initialized in the application layer task and implement an I/O messaging mechanism. All functionalities are encapsulated as I/O events, which are processed in the corresponding message handlers. 1. An original MSG is sent from Universal Peripherals ISR or BT stack. The processing flow is as follows. A MSG from peripherals is forwarded by MSG distributor to I/O MSG handler for handling. B. MSG from BT stack is forwarded by MSG distributor to BT state machine. BT state machine handles MSG and sends a BT I/O MSG. MSG distributor receives the BT IO MSG and then forwards it to IO MSG handler for handling. C. After a message is received, IO MSG handler shall make judgment and call the related event handler. 2. Developer programs shall implement peripheral ISR, complete preliminary processing in ISR, and package MSG to send to app if further processing is required. B. Maintain IO MSG handler to receive and handle MSGs defined by developer. C. Implement event handler about application. 3. Gap layer notifies app layer with MSG and event mechanism, while app layer calls gap layer function by APIs. ROM, read-only memory. Used to store fixed data and programs. Contents are written during manufacturing and are usually not modifiable. Commonly used for storing boot programs, firmware, and other data that does not need frequent updates. RAM, random access memory. Used for temporarily storing data and programs. Allows for fast data reading and writing. It is volatile memory, meaning data is lost when power is cut off. Cache. A type of high-speed memory. Stores the most frequently accessed data and instructions. Designed to speed up data access. Flash memory. A non-volatile memory type. Can be erased and rewritten multiple times. Commonly used for storing operating systems, firmware updates, and large files. eFuse, electronic fuse. A programmable read-only memory. Used to store one-time configurations or keys. Once programmed, information cannot be modified or erased, providing a secure storage mechanism to prevent tampering. BLE SoC series are integrated different CPU and cache strategies shown on the table, which decides different memory map. The different ICs have various types of memory as shown in the table. RAM is further divided into TCM, data RAM, and buffer RAM. For more details, please refer to BLE SoC Memory Introduction. The memory map for the RTL87X2G is as follows. 1. 512 kilobytes of ROM. 2. 384 kilobytes of RAM. 3. 16 kilobytes iCache. 4. 32 kilobytes dcache. 5. Up to 64 megabytes of flash. 6. 1 kilobyte of eFuse. The memory map for RTL87X2E and RTL87X2H is outlined as follows. The key difference is that RTL87X2H supports larger ROM and RAM capacities compared to RTL87X2E. The memory map for RTL87X2D and RTL87X2C is outlined as follows. The main difference is that RTL87X2D supports larger ROM and RAM capacities and has an expanded flash mapping space. RTL87X2X NVIC features. 1. 8 programmable priority levels. 2. Support vector table relocation. 3. Low latency exception and interrupt handling. 4. Implementation of system control registers. 5. The differences in the number of exception and interrupt channels among various ICs can be seen in the table below. The NVIC and the processor core interface are closely coupled, which enables low latency interrupt processing and efficient processing of late arriving interrupts. All interrupts including the core exceptions are managed by the NVIC. RTL87X2X supports 3 fixed highest priority levels and 8 levels of programmable priority. The usage scenarios for the priority levels of different chips are shown in the table below. RTL87X2E/RTL87X2H supports 3 fixed highest priority levels and 4 levels of programmable priority, but for compatible with RTL87X2C and RTL8762D, 8 levels of programmable priority are used. The larger the number, the lower the priority. But the priority used on RTL87X2E and RTL87X2H, 0 is equal to 1, 2 is equal to 3, 4 is equal to 5, 6 is equal to 7. The Power Management module manages the platform and Bluetooth as two separate modules. The platform low power mode is designed to manage the power usage of various components such as the CPU, RAM, peripherals, and clocks to optimize energy efficiency. There are three main power modes mentioned. Active mode. This mode provides ultra performance with a high-speed clock and relatively high power consumption. It includes two submodes. CPU active. The CPU operates at a high speed, ensuring maximum performance. CPU sleep. The CPU enters a sleep state with the clock automatically slowing down to reduce power consumption. This mode supports quick wake-up through interrupts. DLPS, deep low power state. This mode offers lower power consumption while allowing for relatively fast entry and exit times compared to active mode. RAM content is maintained in this state, making it suitable for situations where low power consumption is needed, but the system must be ready to respond quickly. Power down. This is the ultimate low power mode aimed at minimizing power consumption to the lowest possible level. It features a relatively long exit time, as the system powers down many components to achieve maximum power savings. In this mode, RAM contents are not retained, meaning data stored in RAM will be lost unless it is saved elsewhere before entering this mode. These modes enable the platform to balance performance with power efficiency depending on the operational requirements at any given time. For more details, please refer to BLE SoC Power Mode Introduction. The BLE SoC series chips are iterated according to their respective product positioning, resulting in different types of firmware. Below is a summary of the RTL87X2X firmware types and their functions. 1. System configuration file. Records information about hardware configuration and Bluetooth configuration, such as configuring Bluetooth address and changing connection numbers. Can be generated through MP tool. 2. OTA header file. Defines the bank layout of the flash memory. Generated by MP pack tool. 3. Secure bootloader image. Released by Realtek to optimize the boot process. Must be programmed if OTA update bank switching is not used. If bank switching is used, it is not necessary. 4. Boot patch image. Only exists in the RTL87X2G, replacing the secure bootloader image type. Includes Bank 0 and Bank 1 boot patch images, released by Realtek. The entry points for patch functions are retained in the ROM code, allowing the original behavior of the secure ROM code to be modified or extended through patches. 5. ROM or system patch image. Released by Realtek. Allows the original behavior of the ROM code to be modified or extended through patches. 6. BT stack patch image. Released by Realtek. Can extend ROM code features through patches and provide support for stack-related features in the BT controller. 7. App image. A BLE application developed by developers. 8. BT host image. Implements the upper BLE stack. 9. App configuration file. Records application configuration information, such as gap configuration. Can be generated through MP tool configuration. Users can download files using MP tool or MP-CLI tool, with MP-CLI tool being the cross-platform version of MP tool. MP tool has two downloading modes, MP mode and debug mode. MP mode is suitable for mass production. For more information, please refer to RTL87X2X MP tool introduction. RTL87X2X supports a variety of debugging methods. 1. SWD-based online debugging. The SWD debug protocol supports basic debugging functions, such as run control, setting breakpoints, and accessing memory. 2. Log mechanism. The debug analyzer is used to trace the execution of applications by printing logs, capturing BT data, and further analyzing it through third-party BT analysis tools. 3. Hard fault analysis. The hard fault handler uses logging tools to print and save CPU registers, R0, R12, LR, PC, XPSR, OS-related status information, such as the currently running task, TCB, and top-of-stack and RAM memory details to trace and identify the root cause of the issue. The purpose of system tracing is to enhance the system's debugging and monitoring capabilities. By using periodic software timers, hooks, and watchdog triggers, it tracks information related to task stacks, heaps, queues, and timers during application execution, as well as the LR and PC when a task watchdog timeout occurs, and the reasons for failures to enter or wake from DLPS, deep low power state. This process is primarily used to analyze system resource usage, diagnose issues such as task hangs, and address problems related to not entering DLPS. For detailed information on debugging methods, you can refer to BLE SoC Debugging Introduction. The above content is the complete introduction to the BLE SoC SDK. Thank you all.